in the previous class, we were looking at the three-phase circuits, right? And specifically, we looked at the types of connections, namely star and the delta type of networks. And after that introduction, we actually had an analysis of the star type of network. Okay, and in that, we basically try to relate the two quantities, namely the phase voltage and the line voltage. Also, we try to relate the line current with the phase current of a star type of network. All right. So we'll continue from there. So next we'll do the analysis of the other type of network, which is a delta, right? So the analysis will remain pretty much similar to that of the star type of network. Okay, only the relationship between the line voltages and the line currents are going to change. Okay, so other than that, everything else will other topics will remain pretty much similar. Okay, so let's start with drawing the network. So this is, let me mark the three different points first. So these 3 points I want to connect. Okay, so that's one particular the impedance, the load. Okay, so we connect that between two of the points that are already selected. Okay, so this is the one. This is one particular line of the load part. Similarly, we will be writing the other two as well. Okay, so this is the second one. Okay, then okay, so this is a load number 3, right? So let's give some names. Like this is, say, let's say A. I will call this as B, and we'll call this particular node as C. Okay, and already we have seen that this is, say, A, and this is C, and I also need a B. Let me try to write the B over here. All right. So this is A to A. If I call this also A, this is a line. Then if I say B here, B to B, that's a line. Then I'll write C here. So those are the C to C is a line. Okay. And let me try to write the values of these loads connected to be purely resistive. And let us say that that is equal to R. Okay, so now the currents that are going to flow in the lines, let's mark them first. So this is IA. There's a current flowing here, which is current flowing here. I'm going to mark as IC. And we need to measure the different voltages between the lines as well. So this AB is what? Okay, let me write as per the convention. This is VAB. I also have voltage between B and the C. So we'll call it as VBC, and we have the line voltage between the lines. So this is VCA. All right. So those are the line voltages which we have measured. So put the sign convention to that. Okay. Right. So also we have to measure the voltages, not volt, oh yeah, voltage as well as currents along the phases, right? So let me try to mark a current here. I'm going to call it as IAB. Let me mark another current here. This is IBC, and another current over here. This is ICA, and we need to measure the voltages as well in the along the same loads. So I'll call this itself is, now if you see again, this is between VAB itself, right? So I have to give a name same. So this is plus minus VBC, and this is plus minus VCA. All right. So this is what is the circuit that is required. Uh, Yeah, here in this case, you see, this is what is marked as C, this is marked as A. Whatever is between these two, right, that is what we are measuring here. I'm connecting a resistor and I'm trying to measure the voltage across that. It is denoted as CU. Okay. Now, in case of this delta circuits, there are actually the same voltage that is that actually appears between the lines as well as the phase. Right? VCA means both are VCA only, right? You have the same names coming into picture, right? So that's a speciality of delta type of network. Okay, anyway, we'll come to that. So before that, let's try to do the analysis part, right? So that is consider the delta type of connection using three resistances R. Okay. Now, so let me try to denote the IB, IC, right? So I can see that they are the line currents. All right. So line currents, let's try to denote using the IL as well. Okay. Also, I can see IAB, IBC, and ICA. Okay. So those are what? Those are the phase currents. Right? So since they are the currents flowing through the phase, let's call them as IPH. Okay. So these are the same what you call the same notation that we have applied so far. Okay. Now I want you to apply. Let us say Uh, okay, let me take a node. I'll say this is a node A. I'll take node A. You can even take B or C as required. No problem. Right. I want you to apply the nodal analysis, or even you can apply the KCL. That's fine for it. Right. To relate these currents IA, IAB, and ICA. All right. So I want you to apply the node, either node analysis, or you can even call it as a Kirchhoff's current law. And at a node, you can apply the relationship. You can try to find out the relationship between the currents that are entering and the currents that are leaving the node. Correct? So according to the KCL at node A, I can say that current entering, there are two currents entering and there is one current leaving. Correct? So IA plus ICA is equal to, I can say, IAB, isn't it? Okay, let's write that. At node A, applying Kirchhoff's current law. Current entering, one is IA and one more is ICA. That is equal to current leaving the net, that node is IAB, isn't it? So let me try to write it in this way. If at all I want to calculate IA, right, then I am supposed to do IAB minus ICA. Is that okay? Right, I'll move the ICA to the other side. Okay. Now this is actually a proper notation which is required, because you see here, this is what, this is the line current. Okay, and on the right side I have the phase current. So I'm trying to relate the line currents and the phase currents all over here. Okay, fine. So let us do the similar analysis we did earlier by doing the using the phasor diagram. Okay, yes. Drawing the phasor diagram. Right. So our next intention is to draw the phasor diagram. Okay, so let me draw that. So this is, let me call this is IA. Right. So then I'll also mark another one over here, and the third one, which is on the, which is the, yeah, always they have to be 120. So if you remember our basic discussion over here, you see that it can be voltage waveform or the current waveform. So angles, the phases of individual waveform should be separated by 120 degrees. So no gap, the gap between them is 120. That's all. It can be the orientation can be anything. So I think already, I also have tried to write that somewhere. You see here, see, it can be anything, right? So like this you can draw, like this you can draw. So anywhere you, any type of representation you give, right? The gap between these three different vectors should be 120. That's all. So if you start from here, you add 120 to that. So you see this is completely different than what I have drawn. But still you need to take care that this all the three angles should be 180. Sorry, 120. Okay, so that's how it is. Anywhere you want, you can draw. No problem. Right. Okay. So okay. So let me. I think let me just go back and check the equation once. Equation says IA is IAB plus ICA. Okay. So I need to talk in terms of IAB and the phase currents. I'll write. Okay. So IAB, then IBC, and IC. So if you look at the equation says that you want to calculate IA means consider IAB and take minus ICA and add them together. Correct? So what I need minus ICA. So if this is what you call as, if this is what you call as ICA, where should be the minus of ICA? On the opposite side, correct? So that actually like this. So this is what I'll write. This is minus IC. So now again, IAB is a vector, ICA is a vector. So minus of ICA is also another vector. So I ultimately want to add the two vectors. So the best suitable method is right by using the law of parallelogram. Correct. So you need to complete this parallelogram. So let me try to draw that. Okay. So this is right, the one which is parallel to the minus ICA. Okay, I also have to draw another one which actually is parallel to IAB. So this is the one which is parallel to IAB, right? So once you are ready with this, the diagonal is nothing but the result. So let me change the color for this. It actually starts from this point, and this is the result of that addition which we were trying to do. Right. So what is that? If I try to mark the vector that is IAB minus ICA along this blue color, that should be what? That should be IA, isn't it? So this has to be IA because our equation says IA is equal to IAB minus of ICA, right? Okay. According to that, we have drawn. Now what we'll do, we'll try to calculate the angle so that we can calculate the required length of IA, right? So if you remember, this is how much? So yes, so this angle is 30 degrees. This angle is also 30 degrees, right? And we know that we will be drawing this perpendicular. Let me call this length as say x, and this length as what? So normally, right, we'll try to make a calculation that is IA is actually equal to x plus y, correct? But if you want to calculate this distance x, I know IAB cos 30, correct? This is IAB cos 30 plus the next part that is y. Y is actually equal to, this is IA. Is it IA? Sorry, it's ICA. No, okay. So this is ICA. Let me correct. Okay. So this is ICA cos 30. Correct. So what I can write here, what is IAB? IAB, sorry, on the left hand side, IA, right? IA is actually a line current, right? Line current is equal to IAB, which is a phase current. This is IPH cos 30. Cos 30 is how much? Cos 30 is root 3 by 2. IPH root 3 by 2 plus another IPH root of 3 by 2. So root 2 times of this, so I can simply write this is root 3 times IPH is IL. So line current is root 3 times the phase current. All right, so that is the basic equation that relates the various types of currents in the delta network. And for a delta network, I already have some idea about the relationship between the line voltages and the phase voltage. So the line voltage is VCA. Same thing is available across the phase voltage, right? Across the phase components. So line voltage and the phase voltage are same. Okay. So also for delta connections, right? The VL is equal to VPH. Okay. All right. So we have done the analysis of this delta network with this. All right. Do you have any doubt? Let's go ahead. The next topic is the power measurement. Right, so we'll look at how the power can be measured. Okay, so basically we know that if you have a single phase circuit, right, in general, the equation to measure the uh, average power of a single phase is given by, right, normally it's a phase, right? So phase means you always use whatever voltage that comes across the load into the current that comes across the load. And if the load is non-resistive, in the sense it can be impedance, any impedance, you will consider the power factor. So if you remember the basics of the single phase AC circuit, how do you measure the average power? Voltage into current into the cos phi, or the power vector, right? So that's the basic. From there we start now. Okay, so this is what I'll write V. Huh, definitely. Yeah, sure, sure. No, no problem. Anyway, I'm for every topic when we discuss whatever is required from the previous one, I just write it as we know that. That means it comes from the previous chapter. Okay. Right. So now already we know this means it's actually coming from the previous chapter. So that is what I'm trying to recall here is the average power. All right. So that is average power of, it's a single phase, average power of a single phase circuit. Let me try to denote that. Maybe I'll call it as a P1. Okay. So the notation I'm going to give here is P1. All right, so P1 is equal to, so you just have to remember that you will take the voltage into current, V into I is the power, but that actually holds true for a DC circuit. But if it is a single phase AC circuit, you need to multiply by the cos phi, right? Where cos phi is called as the power factor. All right, so I'll write it as V. Now you see I'll write pH because I'm measuring with respect to a phase. So phase component, so VPH into IPH into, this is cos phi. Okay, very straight equation, right? VI cos phi is the general equation, but right now we are writing very specific to the single phase circuit. All right, so I'm going to call that as equation number one, right? So where phi is called as the lead or lag angle of the load, or simply you can call it as a phase angle of the load. Okay, so this is what is the first step. Okay. Now let us assume that I am connecting three different balanced loads to get a three-phase circuit. All right, so three such loads are connected, doesn't matter which type of, which format it is, but you ultimately get a three-phase circuit. Okay, in such case the total power should be VPH into IPH into cos phi multiplied by 3, because you have three such loads, same current VPH, sorry, same voltage VPH, same current IPH, same lead lag angle, or the phase angle that is given by phi, right? So for per phase, this is the equation, that is equation number one. Since you have three different such connections, or three different loads connected to form a three-phase circuit, I need to multiply by 3. Okay, so therefore, if that is the case, then let's consider for a balanced load, total power in a three-phase circuit. right? Let me try to denote that as the PT. PT is the total one, okay? So total power should be 3 times, I can call it as P1. P1 is the actual uh, value that is written in the equation 1. So PT should be equal to 3 times VPH IPH into cos phi. Are you okay? So let's hold on to this. This is equation number 2. Right. For let's now switch according to which type of network that we are talking about. Right. So let us say this is, I'm going to be specific about the type of connection that I'm going to make now. Say for star. Yeah. For star network, I have an idea because now you see, normally the phase values, whatever we have written here, like VPH, IPH, etc., are known only if you are present at the load location, wherever is a load, right? Because practically talking about any electrical circuit, right? So the source and the loads can be thousands of kilometers away, like the example I gave in the previous class, if you remember. So the source could be the power generation point, right, for a complete city, which can be 500 kilometers away from the city, right? The whole city is going to look like a impedance for that particular source. But this, if you look carefully, the city will be somewhere, maybe as the same example, 500 kilometers away from the power generation station. Okay, so unless and until I am at the city and I know the values of what resistance it looks like, I have no idea about what is the V phase or what is the I phase. Okay, but on the other side, if you are located at the power generating station, you will have a clear idea about what is the line current and what is the line voltage. Okay, between a line, because you are sending the power through a line, you know how much current you give, how much voltage is there between the lines, because three lines are there, you are generating three different different voltages and you are sending across the three lines. You can measure the line voltages and the line currents. So it is always suggested that you try to write this equation in the form of line components rather than the phase components. Okay, so though we have applied to get the equation number 2, we basically applied what we knew from the first chapter, that is the AC circuits. But now the physical requirement is that it is not suggested to write it using the phase components. It's important that we convert everything into the line component. Okay, so what I try to do for a star network, we already know that the V line is equal to root 3 times V phase, correct? Also, I know that because I want to bring the line into picture here. So every V phase, you are going to write it as VL by root 3. And I know that the line current and the phase currents are same, right? For star network. Okay, are you able to recall this? So I'll quickly show you the star one. You see here? Okay, so this was the star network. And for a star network, VL is equal to root 3 VPH and IL equal to IPH. This was from our last discussion. Okay, so I'm using the same things over here. Okay, same points I'm using there. So this is what I want to put back in the equation number 2. So this implies the equation number 2 becomes equal to, on the left hand side I have the total power, that is equal to 3 times every VPH. I'm going to write it as VL by root 3 because I want the whole equation to be represented in the form of line parameters only. And every IPH I can simply write it as IL. Cos phi remains as it is, correct? So that means the total power in a star network can be measured using, so root 3 cancels with the 3 as root 3 times VL IL cos phi is the equation. Okay, right. Let's go ahead, do the same thing for a delta network. Right. For a delta network, we know the following, right? At the beginning, we actually had prove this. So VL is equal to root 3 times. Is it that? Sorry. VL equal to VPH. VL equal to VPH, right? Perfect. VL is equal to VPH. And the other relationship is nothing but IL equal to root 3 times IPH, right? Now I don't want any IPH to be present, so I'll make a substitution for every IPH as IL by root 3, right? So once again, the equation 2 becomes the total power PT is equal to, there is 3. I have VPH can be directly written as VL. Every IPH, I need to write it as IL by root 3 into cos phi, right? Once again, this root 3 and the 3 gets cancelled as a root 3. So this is root 3 VL IL cos phi. So the point here is that irrespective of, yeah. So they're same in the sense, you know, the line voltage means that itself is the phase voltage for a delta net, but that is not true for the star net. Okay, if the network is a star network, IL and IPH are same, but VL and VPH are not same. If you are considering a delta network, VL and VPH are same, but IL and IPH are not same. But though it is, as of now, what we understood is that the line voltages and phase voltages depend upon what type of network you choose. But important point here is that the total power equation still remains same, right? You can see that this is for a star network, this is for a delta network. Both equations are same. Okay, power can be calculated using the same equation. That is, total power is equal to root 3 times VL IL cos phi. That's all. So that is the equation that you need to use to calculate the power in any three-phase network. Is it okay? All right, let's move ahead. Now, okay, let's move further. Let me write the side heading, then we'll discuss. So we have to see how can you measure the power. So that is power measurement using 2 watt meters. Okay, so have you heard of a device called watt meter? So watt meter, yes, watt meter is a power measuring device for any circuit, right? For any circuit basically refers to, let me say there is a, this could be a single phase AC circuit, right? I might have resistor, inductor, capacitor, or whatever present over there. So in order to measure the power inside this particular circuit, power that is actually getting delivered to the load, I can connect a watt meter over here, and that watt meter will show what is the amount of power. Okay, so the fundamental logic is that if you have a single phase circuit, you need 1 watt meter. So per phase, you need how many? You need 1 watt for every phase. So now basically that means I have let us say a 3-phase circuit. 3-phase circuit, as the name suggests, there are 3 different phase components, 3 different resistors. Okay, so once you have 3 different resistors that are present in your circuit, in order to measure the power across each of them, you need how many watt meters? You need 3 watt meters. Correct. So 1 watt meter per phase. That's what is the fundamental logic behind using a watt meter. Watt meter works on that principle itself. You need 1 watt meter per your circuit or something. Okay, per phase. So since you have 3 phases, it is always expected that you are supposed to use 3 watt meters for power measurement in a 3-phase network. But what happens here is that if you make the connections of the watt meter very properly, you actually don't need 3 watt meters. Okay, to measure the power in a 3-phase network, you need only 2 watt meters. That means you actually save some connections, you save some power resources. Okay, so that is what is the concept, right? How can we connect only two watt meters to a three-phase circuit and we can still be able to measure the total power in that three-phase circuit very accurately, right? Is what is this concept. Okay, all right. So, right, let's we need a slightly different circuit over here. Okay, let me draw it. Okay, so somewhere at the center. Okay, let me draw one line over here. So I will draw one phase component over here. Okay, and then I'll continue this. Let me take this point as my main point. Then I will draw two more lines, one here and let me say one towards this. Okay, in that I need two more. Okay, so that's the second one. And let us see, I'll draw. Okay, so this is the star network that we are considering. All right. So let me call this is A, this is B, and this is C. All right. Now this is say IA, this is IB, and let me mark this is IC. Okay, so as usual, I'll call this point as A, this point as B, and this is the point which I'm going to call as C. Okay, so it's a star, so I can know I can identify a neutral line, neutral point, right? So if I assume this is how it is, so plus minus this is VAN, so this is plus minus VCN, and this is plus minus VBN. Okay, now let's come to the watt meter. Okay, so this is how a watt meter looks like, right? So watt meter, so you see, watt meter means wattage is for power, right? So what is the power equation? Basically, power equation is nothing but voltage into current, isn't it? So when I say I want to measure voltage and current in a circuit, from the basics of electrical or electronics, you can try to answer this. If you want to measure the voltage, right? Or so what is the device that measures the voltage? It's a voltmeter, correct? Voltmeter is always connected series or parallel, right? So you have to measure means you have to connect it in parallel, right? For a resistor, see, I'll tell you the meaning, right? So if I want to measure the voltage across this resistor, right? So I have to connect, I have to make sure that I will use a voltmeter for sure, but you will connect the voltmeters plus terminal here, minus terminal here. So one wire comes here, one wire comes here, and you will be able to measure a reading here, right? So that means you are measuring in series or parallel. Parallel. Okay, so voltmeters always are connected in parallel. So basically, if you want to measure voltage, you need to connect a device parallel to the device where you want to measure. Okay, at the same time, right? I want to measure the current that actually flows in this part, in this particular line, right? What you will do, you will basically, right, open that particular line because you want to measure the current on this line. So what you will simply, you can, what you'll do, you'll open up this, okay, and you will connect an ammeter over here. So current enters into the ammeter and current leaves the ammeter, so that you can see this on the screen of this ammeter saying how much current is flowing. Okay, so are you connecting this in series or in parallel? You are connecting in series, right? So for measurement of currents, right, you need to connect the device in series. Okay, so that was the fundamental concept. Now let's go back. So the point here is I am connecting a wattmeter. Wattmeter basically should read the current, should read the voltage, take a product and should display. Correct? Because wattage is what? It's a power. Power is voltage into current. So the wattmeter basically has three different terminals. Okay, for the same purpose, right? One set to connect it in series to measure the current, and another to connect in parallel so that you can measure the voltage. Okay, let me show you. So this is how the wattmeter connection should look like to us. So I'll just open up this part. I'll also open up the bottom. Okay, now you see here I'm actually connecting the wattmeter, but the wattmeter connection looks in the following fashion. So you basically have a coil. Sorry. Basically, you have a coil. All right. So coil in the sense you are right like an inductance. It's a coil. There are two different coils that are located that you can find inside the wattmeter. One particular coil is, this is the coil which I'm going to call as a CC. CC for current coil. Right. You see you are connecting it in the series. That means current coil is used to measure the current that is flowing over there. Okay. I need another coil that should measure the uh, the current, the voltage. Correct. So I'm connecting over here. You see here again, this is a parallel connection, though it looks like a series. So this is the one, right? And you can have, right, you can connect this. Maybe I can show you one resistance over here, some small resistance just for internal purpose. Okay, and you connect it like this. Now you see you are connecting in series or parallel. This is parallel connection, right? So starting from this point I'm connecting to a different point, so I'm actually connecting parallel to this device. Correct. So this current coil is in series with this. It measures the current flowing through this particular component. Okay, and the second coil which we have written, yes, it's called as voltage coil or a PC. I think PC, potential coil is the actual name. Okay, potential is voltage, right? So you have a PC communication, right? So all together, uh, this is a resistance. Okay, even if you don't write, doesn't matter. All right, there is some resistance of this wattmeter, right? So we are trying to write that over here. So whatever you see inside this red colored box is the W1, wattmeter number one. Okay, so that is wattmeter number one. I need to write the similar wattmeter number two because we are trying to measure the power using two wattmeters. So what is this? This is the current coil CC, and I will have a similar the potential coil that is located, right? So I can take like this, and let me try to write another coil over here. Okay, so this is the other coil. This is the potential coil of the second one, and I can also try to write this is just a representation. Okay, so you can have some resistance that is present for this whole watt meter. That's what is denoted here, and I'll make the connection to this. Okay, so that is the uh, connection, and again this is the watt meter number 2. I'll call as W2. So you see the overall big picture of how to make the connections. So now, yes, correct, I'll come to that point. So your question is now, how do you measure the power, that is the current, and the voltage that is required to be measured across the third one, right? So that is our fundamental idea. We have to prove that, right? I have to prove now that, okay, if you make a connection of W1 and W2 like this, you are not just calculating the powers of these two, but also this is what is our target now. Okay, so this itself is a connection that is required, using which we still be able to measure the required total power across all the three resistances, not only the two resistors. Okay, all the three will be considered. We need to prove it. All right. Okay, right. So this circuit diagram is fine for you, right? Okay, let me go with the explanation so that things becomes more clear. Okay, so let me write one sentence about this circuit. Let there be three load resistances of value that is equal to capital R, which get connected in star connection in the figure or diagram. Okay, so three resistors are taken and connected to form a star network. All right. Now, the we also have to tell that how you are connecting the wattmeters. Okay, so let the 2 watt meters, we already have given names. One is W1 and the second one is W2, right? Are okay, let's say are connected such that, right? Okay, now we need to be careful about the connection. You will connect the current coils of those wattmeters along the lines, right? Along the specific lines. Now you see what are the two lines you have connected, right? What are the two lines where you connect the CC? CC is connected along A and B, correct? Along this is line A, along this is line B. Line A and line B, you have done this connection, isn't it? So such that their current coils, so I'll write CC, are along lines A and B. That's the first thing. And where are the potential coils? And the potential coils are, okay, we cannot write along because you are connecting parallel, so you will write across, right? Across, for the first one you are connecting across AC, okay, and the second one is across BC. So just make sure that that's how it is. So A and C you are connecting a potential coil, okay. So similarly you have connected the second potential coil that is between this B and the C, across the BC. Is that okay? Fine. So we simply try to explain what we have drawn in one or two lines. Right. Now, let us try to give the notations that are required. Only required part will use it. Okay. So let I need IA, IB, and IC. Right. What are they? They are the line. So they are the line currents. Okay. So I will write it as IL. But if you see, this circuit is a star network, star kind of circuit, that where IL is equal to IPH. I can definitely use if required. Okay. And I also need VAN, VBN, and VCN. What is VAN, VBN, VCN, etc.? Each one is a phase, correct? So it's a phase voltage. For any three-phase connection, the same two wattmeters can be used. Okay, it will work even for delta network, right? There are multiple other versions of connections as well, but these are very common, as I told. But yes, to answer your question, answer is yes, it will work for all. Okay. Now, if at all I know the current and I know the phase voltage, what is the total power? Okay, so this implies the total power in three phase circuit, right? I will call it as usual PT. PT is equal to, now without using the watt meters I'm trying to measure. Okay, without using the watt meter, if I want to do the manual calculation, this current into this voltage, this current into this voltage, this current into this voltage, correct? So three currents, three products and a sum. Okay, IA into VAN, that's the phase voltage, that's the power in this phase. So current into this voltage, current, the power in the second phase, plus IB into VBN is the third phase, correct? So total, that is the sum of the, or that's the total power that is present in this. Again, you see, I am not using the wattmeter. Wattmeter is not used. Without using that, I manually I am calculating, let us assume. Okay, right. Now, what my intention is that I use the wattmeters, I should get the same answer. Then only you can say that yes, you can use only two wattmeters, isn't it? Okay, so without using wattmeters, let me try to write that. So therefore, the total power in a three-phase circuit is given by, how you start? You can write current first IA into VAN plus IB into VBN, isn't it? Plus IC into VCN. This is the actual power that is measured in this particular circuit. Fine. Now let's use the watt meters and try to calculate what both the watt meters do measure, and let's try to take a sum of that, because there are two watt meters. I need to add them together for sure. Okay, but let's do that math now. All right, so we'll hold on to this equation and let the reading of the W1, I'm going to call it as W1B, say some power, we'll call it as a P1. Okay, right. Now you see, what is this P1? The P1 has to be the current that flows through the current coil of this W1, and the voltage that is measured by the potential coil of W. Okay, so this is let the reading of W1 be P1. So what P1 reads is equal to, I'll try to write it in sentence now. So this is actually the current through the CC of W1. Is it okay? CC, current coil of W1, multiplied by the voltage. Voltage across potential coil of W. Okay, so let's try to write that, right? What is the current that is going through? Check this. What is the current that flows through this CC? That is IE. Perfect. So let me write that. So this is IA into what is the voltage across the PC? In the sense, here how much is the voltage? Is it only VAN? Plus or minus, maybe you need to take care of the Kirchhoff's voltage law. So if I move like this, I start from plus, I go to minus. I start from minus, I go to plus. They have to be opposite in polarity, correct? Right. So it's I can try to write it in the following fashion. Now VAN minus VCN. Okay, fine. Into VAN minus VCN. Okay, let me hold down to this. This is equation number 2. Right. Very similarly, there is another wattmeter. So let the reading of the wattmeter is W2 be P2. So again, P2 is equal to, it's the current. Correct. So current through the CC of W2, multiply that with the voltage across the potential coil of W2. Now, what is that? How much? Can you measure both of them? Okay, IB and I'm moving VBN minus VC. All right, let's try to write that. So this is IB into VBN minus VCN. Okay. What happens to IC? I'll come to that. I'll come to that. Okay. So now we need to, now according to our connection, power measured by first one is P1, power measured by the second wattmeter is P2. If I add them together, basically, if by using just 2 wattmeters, if you are able to measure the total power, the sum should come to be this one, correct? Because this is the total power which actually we expect to be measured. Okay, let's try to see that. Okay, so readings of both W1 and W2 means I just have to add P1 plus P2, correct? So according to this, it has to be IA into, this is VAN minus VCN plus IB into, this is VBN minus VCN, isn't it? Let me try to separate the terms. IA VAN plus IB VBN. Then the VCN is common, so I'll write minus VCN common into, this is IA plus IB, correct? Okay, I know that I am actually considering a three-phase circuit, right? In any three-phase circuit, there is a property, that is IA plus IB plus IC equal to 0, isn't it? So that means what is IA plus IB? Equal to minus IC. Okay, use it. Use it in the above equation. So that is equal to IA VAN plus IB VBN. Minus of minus is plus IC VCN. All right. So compare this with the actual equation which we had written very soon. Over here, IAVAN plus IBVBN plus ICVCN. This itself is measured by 2 watt meters as well. Okay, so P1 plus P2 itself is equal to PT. Right. So this P1 plus P2 is giving you the total power in a three-phase network. That means only 2 watt meters are sufficient to measure the total power in a three-phase circuit. Okay, so that is the conclusion. Therefore, only 2 watt meters are sufficient to measure the total power in a three-phase network. Right, basically this total power is equal to the readings of W1 plus W2, or even you can even write P1 plus P2, doesn't matter. So total power is nothing but you know that you are measuring the root 3 VL IL cos phi. Correct? So this is the total power. So PT is equal to root 3 VL IL cos phi. We already have proved that. But if you use the 2 watt meter method, this is the equation which holds good. All right. Then we have one last point, right? So that is actually the measurement of the power factor. Yeah, sure. No problem. Let's take a 10 minutes break. All right. So the next topic is actually the power factor. So if you want to measure the power factor using the 2 watt meter readings, all right. So if W1 and W2 readings are known, then we have one equation that relates the readings with the power factor. That is tan phi. Phi is the power factor which we want to measure. Okay. Power factor is cos phi. Sorry. First, we'll try to find out the angle phi. Okay. So tan phi has a relationship between the readings of the watt meter. So that is the difference of watt meters W1 minus W2 divided by W1 plus W2. So there is a tan relationship. So if you want to find phi, then that should be tan inverse of root 3 times W1 minus W2 whole divided by W1 plus W2. Okay. So using this, once the phi value is known, this implies the power factor PF is equal to cos phi. That's all. You can find the actual power factor using this particular equation. That's all. All right. Okay. Now it might require, we'll solve the problems. Okay. So the theory concept we have completed, right? So directly we'll start solving the problem so that you will come to know about everything that is required to solve the problems of this chapter. Okay. All right. So problem number 1, a three-phase 400 volts power supply is connected across a load of balanced impedances, each consisting of 32 ohm resistance and 24 ohm impedance. Inductive, sorry, let me not write the impedance, inductive reactance. All right, now the question is to find current drawn from the load. Is it load? Sorry, I think I have drawn from the source, my mistake, because we are drawing the current from the power supply, right? Okay, so find the current drawn from the source or the power supply if the impedances are, part A of the question is Y connected, and part B of the question is they are delta connected. In the sense they are connected in Y means what is the current? Yeah, okay, that's a star. And otherwise delta means what is the amount of current. Okay, so this is a question. All right, so just take 1 minute of time to understand what is given and what is asked. Okay, so meanwhile, let me try to write down what is given over here. Okay, so sorry. So it says there is a three-phase 400 volts power supply is connected. So now you see in any of the questions, whenever you say a supply value is given, that is basically the line parameter. So you see here they have given a VL, line voltage is given, that is 400 volts, because to whatever is your connection here, delta or star, this connection gets a 400 volts supply from the source. So that's what is given. So I have to understand that this is nothing but this is a line parameter. Okay, so that's VL voltage. So VL I write. Balanced load of 3 impedances. They say that okay, there is an impedance coming into picture. So that is equal to, how do you write, R plus JXL, correct? Because it is inductive. Inductive is positive. So resistance is given, that is equal to 32 plus J24. Now, basically, I need, in order for to do the complete calculation, right, I need a Z value, right? That is magnitude of Z. So calculate magnitude of Z. How do you calculate magnitude? Root of R square plus XL square. So that is root of 32 square plus 24 square. All right. So can you give me this value? Take your time, no problem. 1640, right? 4440. Yeah, 40. Correct? All right. Okay, so 40 ohms. Now let's take, I think whatever we can calculate, we already have calculated. Let's go to the party of the answer. So that is Y connected. If at all the impedances are Y connected, that means I know something. The VL is given, VL is 400 volts. So what is VPH? VL by root 3, correct? So that is equal to 400 divided by root 3. Okay, please calculate. Okay, 230.94 volts. Okay, that is a phase voltage. Now, if you know the phase voltage, I can calculate the current in the phase, right? That is V phase divided by the magnitude of the Z, isn't it? So that is 230.94 divided by how much is the Z value? 40, right? Okay, that is 40. So you get a value that is 5.77 amperes. That is a phase current, but the question is to find the line current, isn't it? So for a Y network, IL is equal to IPH, right? So IPH is already calculated. So 5.77 amperes is the final answer required for a Y connected network. Okay, are you fine with this? Okay, I want you to try the second half. Anyway, we'll solve together. We'll verify the answer together. But I want you to do the part B, for considering this to be a delta connected network. Yeah, delta connected, right? Yes, perfect. So yeah, I will write along with you. So we know that the phase and the line are same in terms of voltage, so that becomes equal to 400 volts, right? So once you know the phase voltage, you can calculate the current in the phase. V phase. No, I don't know IL. I'm supposed to calculate IL. So I know the VPH. VPH by Z should give you the answer. 400 by 40. So 10 amperes. Okay. Now you know the IPH. You can calculate the IL. IPH is IL by root 3. So I need IL. So IL is equal to root 3 IPH. So 10 root 3. 1.7, so approximately 17.3, I guess, amperes. Is that fine? Okay. Okay. So this is one type of problem which is very simple. Okay. Along with these kind of questions, like given the values of impedances, they can add the questions like power factor, total power, etc. Right? Well, now the question was just to calculate one of the parameter, which is line current. Okay. Now we'll solve another problem, which actually is the next level problem under the same category. Right? You will be given the either the resistance or the impedance or something like that. But the question is not only to find out the line current, power factor, total power, etc. Right? Okay. So then this is the next question. A 400 volts, three phase supply is connected to balanced load with 20 ohm resistance and 15 ohm inductive reactance. Okay, find line current. This is pretty similar to what we have done, but the next part we have not done. Okay, power factor and total power. If you have two parts, A is the star network, B for the delta network. Yes. So as you can see, right, the power supply voltage is given. So whenever the supply voltage is given, it is always taken as the line voltage. VL is 400 volts. So directly let me start with part A answer. That is considering the star type of connection. Yeah, impedance is definitely needed, right? Yeah. Sorry, I missed that. So calculate a magnitude of Z, that is equal to root of how much? 20 square plus 15 square. Yeah, please give me that value. 625, then it's a perfect square, 25. Okay, right. We will calculate the VPH first, that is VL by root 3. Okay, 230.9 volt, that's volts. Right, that's a VPH is known. Calculate the IPH. Right, so that is divided by 25. 9.237 amperes. I know that it's the same as the IL, right? Okay. Now we need to calculate the power factor. So PF is actually the cos phi, right? Again, I don't have the what do you call wattmeter readings over here, right? So I cannot use that. That's one technique. You can do that. Otherwise, you can do the resistance by impedance. This is another method. If you remember from the first chart. Same thing. You get the same answer. So this is R by Z. Okay, R is 20, Z is 25, right? This is also going to work in the same. Resistance value in the given Z value, in this Z, right? Resistance value divided by the total impedance. Okay, that is also going to give the same answer. As you told, your method works. This is also going to work. This is a faster one. Okay, 4 by 5, I think in that case 0.8, right? All right. Then go for the total power. No, it's a constant. Right? Then total power PT is equal to root 3 VL IL into cos phi. Root 3 line voltage 400. What's the line current we obtained? 9.237 into 0.8. Please calculate. Five, yeah, possible. It's in kilowatts, right? 5,119 point something, right? Okay, 66 watts. So 5.12 kilowatts. Perfect. No problem. Right. Normally, these answers powers will come in kilowatts. Okay, don't worry. Even larger kilowatts will come, like 20 kilowatts, 50 kilowatts. All are fine. Okay. So I think now we are solving the delta, right? So this is the delta networks are actually giving more powers. Now you see the answer. Okay, delta for delta. Let's solve. You will understand. So I know that VL is given. So VPH is equal to VL. I can start with the 400, right? So IPH is equal to, right, that is Z. Z is already known, so that is 400 by 25, isn't it? Okay, this is 16 years. So IEL I can calculate as root 3 times IPH. Root 3 into 16. 16 into 1.7. Ah, okay. 27.71 amperes. Uh, Power factor is not going to change. PF still remains as 0.8. You don't have to calculate. Only this changes. PT is equal to root 3. VL is 400. IL is equal to how much? 27.71 into 0.8. 15,358.44 watts. Yes. Okay. So it's a larger one. Fine. So that's the second type of problem that we get. Let's move ahead. Next one is, all right. So input power measured by two watt meters read W1 equal to 3 kilowatts and W2 equals to 1.5 kilowatts. Calculate total power and power factor. Very simple problem. Okay, maybe just 1 or 2 marks or pretty much lesser marks for this. So total power is simply W1 plus W2. Okay, so uh, 3 kilo plus 1.5 kilo, directly 4.5 kilowatts straightforward. Then okay, power factor is asked, so I can calculate the phase angle first, right? Tan inverse of root 3 times, it's a difference, 3 minus 1.5 divided by the 3 plus 1.5. The kilo gets cancelled, so you don't have to do it. Okay, you don't have to write the kilo in the 3 kilo minus 1.5 kilo divided by 3 kilo plus 1.5 kilo. So the kilo definitely gets cancelled. All right, simply you can write this value. And yeah, first you find the angle phi. Sure, please take your time, no problem. Okay. Okay. 29.98. Okay. Approximate to 30 degrees. All right. No problem. So phi is 30. So power factor is cos phi. All right. So that is cos 30 degree. Root 3 by 2. Perfect. Okay. Right. I think that was a question. All right. So that's another very simple question for lesser marks. Then uh, all concepts can be clubbed together to get a problem like this. Okay, the next question actually takes care of everything we have discussed. So this includes the two watt meters as well. So two watt meters read 5.2 kilowatts and minus of 1.7 kilowatts uh, in a three-phase circuit when uh, the line voltage when the line voltage was 415 volts. Yeah, okay. Calculate line current. Okay, so this is the question. Can you try to solve this? Anything that we have discussed in terms of the equations, you can use it over here. All right, try, then we'll solve. All right. So IEL is the question. Let me know where you want me to stop. Okay. Watt meters readings you want to see? This one? Power factor formula or the not needed, right? Okay. So you want me to check the tan? Okay. No, no. Whichever you want. This one? This is the. Sorry. Yeah, this is the one which uses a watt meter. Total. Ah, okay. Uh, uh, no. Yeah. Total power is sum of those two. 0. I think I have a slightly different answer with me. Okay, let's verify. Okay, so what we do here, we'll start with the total power, maybe, right? So total power, how much you get? That is W1 plus W2, 5.2 minus 1.7, correct? Yes, 3.5 kilowatts. Yes, this is right. Then what you calculate is phi value, right? So how much you got phi value here? Okay, 73.67 degrees. And what's the power? Yeah, this is approximately right. I have 73.39. That's fine, no problem. Power factor is, yeah, uh, okay, 0.281. All right. Then you use the total power equation, isn't it? Yeah, I think you missed the kilo. That's all. Otherwise, answer is close. It's a total power divided by root 3 VL cos phi, isn't it? So what is P? What is total power? What is PT you substituted? 3.5 kilo, correct? 3,500. So if you numerator and denominator both have kilo, you don't have to write. Okay, but only numerator has that, right? Denominator has no kilo. So otherwise, right, it will be wrong, right? So 415 into 0.28. Perfect. Yeah, now I think you get the answer. Multiply by 1000. Your answer. Yeah, sure. Take it. Yes, 17.328 amperes. All right. So that's another type of problem. One more we can have. Uh, that should be okay. A balanced delta connected three-phase load is connected to 400 volts source, 20 amperes line current, when 10 kilowatts of power gets absorbed. Find part A of the question. Yeah, so that is impedance of each branch. Part B of the question, power factor. Part C of the question, power absorbed if Y connected. Okay, this is Y. Here's a question. So delta connected load is given, 400 volts line source, in the sense VL is given, IL is also given, and the total power is given. Okay, and they're asking us to calculate the Z value of the phase, ZPH, power factor, and total power if it is Y connected. Okay, okay, yeah, now it's clear. So for part A, we start with the delta connection. So I'll write delta here. So this is for the delta part, first part. VPH equal to VL. So 400 is given, right? And also they are giving the line current. I can calculate the IPH, correct? So IL by root 3. IL is given, if you see, right? 20. This is equal to 20 by root 3. Okay, 11.547 amperes. This is given. Now I can calculate the impedance, right? So the first part, the required impedance, I can call it as ZPH. Okay, impedance of each of the phase. It's very simple. VPH by IPH, correct? Straightforward. So one is voltage, line voltage is the phase voltage, and the current just now we measured 11.54 something. Okay, 34.66 ohms. Magnitude only we get. Okay, so we will not be able to tell that whether there is a capacitor in it, whether there is a inductor in it. No, we cannot. Right, and then what's the second part of the question? Power factor. Yeah, power factor. So PF, right, is equal to, this is nothing but the cos phi, correct? So I can write the P total divided by root 3 VL IL. So total power is given 10 kilo. So 10,000 should be written. Okay. And root 3, line voltage 400, current just given, current is given 20, line current. Okay, 0.721, right? Okay. Yes, 0.71. That's right. So that part is over. Only the last part. Last part says power absorbed if they are Y connected. Correct. So I'll change to star on from this point onwards. So I need to calculate the VPH because line is given VL by root. So 400 by root. Okay. 230.94 volts. So I have no idea about the line current or the phase current. So for this one, IL is equal to IPH here. IPH, how do you calculate? VPH divided by ZPH, because they say that same impedances are connected Y. That's all, right? So 230.94 divided by, we got the value. How much? What was the Z value? 34.66. Yes. 6.66 amperes. All right. Now you know the total power. So PT is equal to root 3 VL IL 6.66 cos phi. Okay, cos phi still remains same, 0.721. 3,300. Okay, 0.82 watts, 3.3 kilowatts approximately, right? Okay. Yes, that's right. So these are the various types of problems that might come. Okay, so small variations in terms of the values are common. Okay, so I want you to practice more problems on from your old question papers if you have any. Okay, so solve that, and if you get any doubt, you please ask me. I'll help you out. Okay, so as far as my knowledge is considered, this chapter can be considered as over.